Okay.
Thanks a lot, 老师。
Okay. And in the test, a regular cyclic load is applied to a specimen, and uniformly, we choose the cyclic load with a stress ratio of -1, like this. This is the cyclic load we have chosen. And through the vertical test, we can obtain the stress life diagram by recording the different cycle stresses and the corresponding vertical life. This is the stress life diagram or the SN diagram. The number of cycles to failure of vertical life corresponding to different stress level. Stress level is recorded as shown in the figure. Each point corresponds to a different stress and vertical life. The stress life diagram depicts stress versus the numbers of cycles to failure. From this figure, the vertical strength of material can be determined. This is a stress life diagram or SN curve for ductile material. Point A indicates the ultimate tensile stress of material which is obtained under static load. From point A to point B, the number of cycles is rather small and the stress is almost constant. And we can regard this rate as a static stress state. And from point B to point C, where the number of cycles is less than the third power of 10, and this is the low cycle vertical stage, and a low cycle vertical behavior is observed. Beyond point C is high cycle vertical stage. The number of cycles is greater than the third power of 10. And the high cycle vertical stage can be split into two parts. The finite life stage and infinite life stage. From point C to point D, the material will thinner for a given number of cycles. The stress corresponding to a number of a load cycle n is defined as vertical stress or endurance limit sigma r n. R is the stress ratio and n is the number of load cycle. Okay. And curve CD can be expressed as this. The m's power of sigma Rm times n is constant. This is for the curve CD. And beyond point D is an infinite life state. The material can withstand load without failure. The number of cycles is infinite. This stress is called the vertical limit. The vertical limit or endurance limit sigma R infinite. Since the number of cycles N D is quite large, a critical number N0 is selected. And the corresponding endurance limit at N0 is termed sigma R. R is the stress ratio. We have this. The m's power of sigma Rn times n is equal to the m's power of sigma R times N0 and it's constant. And m is material constant and decided by test. For shear and bending, m is 9. The stress life diagram curve represents the endurance limit of vertical stress of materials at different numbers of cycles under the same stress ratio. Different stress ratio has different curve. Okay, and when R is -1, the stress is completely reversed stress. We have this. The m's power of sigma -1 m times m is constant. Okay. And we also had this. The m's power of sigma -1 m times n is equal to sigma, the m's power of sigma -1 times n 0. So we can calculate the sigma -1 n. Okay. Sigma -1 n is the is a vertical stress of an element with the stress ratio is -1 and under the cyclic number of n, and then we use the Kn, the life safety factor, to simplify this, and then the stress criteria for material under cycle stress can be expressed as this. And this is the allowable safety factor. And this is the actual stress acting on the element, usually the maximum stress. And zero, we usually choose the 7th power of 10 times. Okay, let's look at an example. A shaft carries a fluctuating load with the endure limit or vertical strength sigma minus 1 is 268. This is the endurance limit sigma minus 1, and under the technical number is N0. Okay, N0 is the 7th power of 10, and the material constant M is 9. The maximum working stress is 240 or 300. And the stress ratio is -1. Calculate the safety factor of the shaft. Draw a simplified SN curve of the material. Okay, so we should calculate the safety factor. And there is you should consider two conditions. When n is the cyclic number is n0, or the cyclic number is the 6th power of 10. Okay, then we load this, then endurance limit -1 n is equal to sigma -1 times this. This is the Kn. So we load the sigma -1 is 268, and M is 9, and N0 is the 7th power of 10, and then we can calculate the sigma -1 n. When n is N0, when then the sigma -1 n is sigma -1 is this. And when n is the 6th power of 10, the sigma -1 n is sigma -1 times this, and it's 346. And then we can calculate the safety factor when n is N0. It's the sigma -1 m over the maximum stress, the maximum working stress. The sigma -1 is 268 over the maximum working stress is 214. So the calculate safety factor is 1.12. This is when the cycle number n is n0. Okay, and when the cyclic number is the 6 power of 10, the calculate safety factor is, use this, sigma minus 1n is 346 over the maximum working stress 214, and the calculated safety factor is 1.44. Use this to calculate the safety factor. Okay, any problem?
Laoshi, can you go back the previous slide?
Pardon?
Here, this sigma minus 1n, that means we are calculating safety factor, right? Safety factor of a shaft.
We use this, the sigma minus 1n over
Yeah, actually this, yeah, actually this minus 1n, what does it mean?
Oh, what does this mean? Oh,
Yeah.
sigma minus 1n. Okay. This. Okay. Okay, let me see. This is the sigma Rn. It's the endurance limit at n. N is the cyclic number, okay? And
Okay.
when R is minus 1, and the stress is completely reversed stress. So this is the endurance limit or vertical stress of sigma minus 1n at cyclic number is n. Okay?
Okay, so is this minus 1 is constant for this position?
Not constant. It changes with the cyclic number. It will change if the cyclic number changes. This sigma minus 1n will change.
Okay.
Okay.
Okay,
And there, if the cyclic number there and there, the endurance limit is different. Okay.
Okay. Okay.
And we from this we know that this is the sigma minus 1. If the number is n0, and this is the vertical stress, the sigma minus 1 and 0. And if the technical number is the 60 power of 10, and the sigma minus 1n is this, it's different. It changes with the cyclical number, okay?
Okay.
And we use this sigma minus 1n to calculate the safety factor.
Yeah.
Okay. Okay.
Okay.
This is the vertical strength under cyclic number n. Okay. And minus 1 is
Fatigue strength.
yes.
Okay.
And this is for the maximum stress is 240. And when the maximum stress is 300, let me see. When the sigma max is 300 megapascal, when the number of cyclic is the 6th power of 10, we can calculate the safety factor is 1.15. But when choose the cyclic number, it's n0, and 0 is the 7th power of 10, the safety factor is 0.89. Is so the element will failure is less than 1. So this will failure, and we can find this point. We can find this point is on the curve. So this is unsafe. Okay, it's not safe under this stress 300. This is not safe. But if we use this technical number, it's safe. Okay, for the maximum stress is 300.
So Laushi, if it's upper than 1, then it's safe, right?
Yes, for this one is safe, but for this n0 is not safe. The safety factor is less than 1. It's not safe. The element will failure.
So if bigger than 1, then they are always safe.
Yes, the safety factor should large than 1.
1, yeah. Okay.
Yeah. Should large than 1. Any problem for this example? Okay, let's continue. And this is the stress life curve or SN curve. It represents the endurance limit or vertical stress of materials of different numbers of cycles under the same stress ratio. Okay, under the same stress ratio. If the stress ratio change, the curve will change. And this, let's do an exercise. Okay. Oh, no. This is too difficult. Let's do this. The vertical strength, sigma minus 1. Sigma minus 1 is the vertical stress under the, with the cyclic number is n0. Okay. 45 steel is 270 megapascal. Assume the critical number of cyclics n0 is this. So use this as n0. And m is line. Estimate endurance stress when n is the first power of 10. So we should calculate the endurance stress sigma minus 1 n. Okay, and n is the first power of 10. Okay, and then we have this sigma minus 1 n is equal to sigma minus 1 times this. Okay, and n0 is this in there, and n is this, and then we can calculate the endurance stress sigma minus 1n is 539. So the answer is A. Okay, any problem? Any problem? The the sigma minus 1 is the endurance stress with the numbers of cycles and 0, and the sigma minus 1n is the endurance stress with the number of cycles n. Okay, and use this to calculate the sigma minus 1 n. So we know that if the number of cycles change, the endurance strength will change. And then the vertical stress, oh, it's the same. Okay. When the parts are subjected to completely reversed stress, so the stress ratio R is -1. The vertical stress of plastic material should be taken which as the strength limit of the material. A sigma B, the ultimate stress. B sigma S, the yield stress. C sigma -1. D sigma over the allowable safety factor. So which one is correct? C. C. The strength limit is the endurance stress. Sigma -1 is for the completely reversed stress. We use sigma -1 as the stress limit. Okay. Answer is C. And sigma B is for brighter material under static stress. Sigma S is for ductile material under static stress. And sigma -1 is for the completely reversed stress. Okay. Okay.
Laushi, sigma S for what? Ductile, right?
Sigma S for ductile materials under static stress. Okay.
And sigma divided by S.
Sigma S is the yield stress. It's for ductile material under static stress. And this is for brighter material under static stress.
Okay.
Okay. Okay, I have below the stress life curve or the SN curve. It represents the endurance stress of materials of different number of cycles under the C stress ratio. And then the endurance limit diagram, the sigma A, sigma N curve is used to evaluate vertical limit of materials for the same life. Usually, the cyclical number is N0 under different stress ratio. Okay, there is different. For SN, the stress life curve is under the same stress ratio, but for the endurance limit diagram, it's under different stress ratio, but they have the same life, means the same cyclic number. Usually we choose N0, okay? And the sigma
তাদের
M,
ঢুকলে টাকা বলে না ব্যাংক থেকে ব্যাংক অফ চায় না
the sigma M is the mean stress.
Yes. सब असले बिल्कुल खिला पूरा टाइम
Okay. Any problem?
ওকে বলে আসলে আপনাকে দিব এই যে একটা সার্ভিস থাকে না ওই সার্ভিস আমি সেটা বলেছি দিব না
M. Sigma M is the mean stress. Sigma A is the stress amplitude. And the sigma A diagram provides a general approach dealing with the mean stress sigma A and the stress amplitude sigma A for high cycle vertical design under axial stress fluctuating. And the curve is obtained from test. In this curve, we have two lines, the Soderberg line A E and Goodman line A B. For each simplified criterion, points on or above the respective lines indicate winner. Okay. And point A represents the vertical limit of sigma minus 1. Sigma minus 1. This is point A represents the endurance limit of completely reversed stress sigma minus 1. Below that, for the sigma M, sigma A curve, the stress ratio is different, but they have the same life. Okay, they have the same cyclic number. And point B is the ultimate stress sigma B, and C is the endurance limit of repeated stress. Oh, there is a little, there is wrong. Not sigma minus 1, it's sigma 0, sigma 0. And the C, the stress ratio R is 0, okay? And for point D, represent vertical limit of sigma R. And point E is the yield stress sigma S. For point A, the stress ratio R is -1. And for point B and E, the stress ratio R is 1. For point C, the stress ratio R is 0. Okay? And the points on horizontal axis represent a static stress state. The points on the horizontal axis, the R is 1, so it's the static stress state. And where points on the vertical axis represent a completely reversed stress, that is R is -1. And line EF represent the stress state where the endurance limit is the same as the yield stress. On the line EF, the endurance limit is the same as the yield stress. Okay, and then we can have the line equation for EF and AF. For if we have this sigma A plus sigma M is equal to the yield stress sigma S. And for line AF, we have sigma minus 1 is equal to sigma A plus push sigma times sigma M. And this is the push sigma can expressed as this. It means stress influence factor of material. For carbon steel, push sigma is in this range, 0.1 to 0.2. And for alloy steel, push sigma is 0.2 to 0.3. And for shear stress, the sigma tau is half of the push sigma. Okay. And points in zone A, F, E, O in this zone indicates safety. So in the yellow zone, the points in the yellow zone is safe. And points outside the zone indicate failure. So, let's have a break, okay? Have a break for 50 or 20 minutes, okay?
好的。
Okay, let's continue.
Yes, Loshi, let's continue.
Okay, we look at points in zoom A, F, E, O indicate safety. If the point is in this 0, then and the element or your design is safe, and outside the zoom is not safe. Okay, and this is the induced limit diagram for material. You should look that it is different from the SN curve. For SN curve, the stress ratio is the same, but for the endurance limit diagram, the stress ratio is different. For point A, the stress ratio is -1. For point B and E, the stress ratio is 1. For point C, the stress ratio is 0. And through test, we can obtain the coordination of point A, C, B, E. And then we can calculate the mean stress and stress amplitude. If the points is in this zone, your design is safe. But for the SN curve, from this curve, we can obtain the endurance limit sigma Rn, and in the within the range of CD. So it's a finite life, and then it's the endurance limit with a finite life in this stage CD. But for the endurance limit diagram, the endurance limit is at N0 is infinite life. N0, we use N0 as the infinite life. Okay. And there are little difference between the endurance limits of material and element. And this diagram is for a material. Because in engineering practice, the geometry, dimension, and surface conditions of a meshing element are usually different from the samples, so leading to a reduced endurance limit. So the endurance limit of meshing element must be modified from published date. The red line A1, C1, F1 is the modified curve for element. Okay, and there are factors affecting endurance limit of element. It includes stress concentration, size of cross section, surface finish, and so on. And this blue line is for material, the red line is for element. Okay, this is the vertical stress concentration factor. It refers to the significant increase of local stresses in the immediate area of geometric discontinuous, such as shaft shoulders, threads, holes, grooves, and notches. And okay, we have this table. And this table is stress concentration factors for a stepped shaft with a shoulder fillet. You can find a similar table on page 36 of your textbook, the table 2.2. Below that, with the increase of this, the the section change will increase and the stress concentration will increase. With this value increase and the concentration factor will increase. And if this is fixed like this, and if this is increased, the size of finish over the size of the means the size of the fillet will increase, and then the stress concentration will decrease. So when you design a shoulder, you should choose the fillet to decrease the stress concentration. Okay. And this is the stress concentration factors of KV on a shaft. Okay, and this is the stress concentration factors for a thread. Okay, and the second factor is size factor, epsilon sigma or epsilon tau. This is for tensile, and this is for shear. And the larger the element, the greater the statistical probability of loss existing with an element, and the more likely the reduction of vertical stress. You can see from this curve in this finger, this is the steer size and the section shape. The white curve represents steer with diamond cross section, and the green curve represents steer with round cross section, and the yellow curve represents steer with square cross section. With the size increase, and the size factor epsilon sigma will decrease. Okay. And the third factor is surface condition factor beta sigma or beta tau. And vertical failures originate from relative weak errors on the surface. Poor surface quality will reduce vertical strength. And the table 2.3 on page 37 of your textbook represent size factors for bending and torsion, and the vertical vertical stress of material increase rapidly as surface quality are improved. And for this picture, after polishing, grading, and finish turning, the surface conditioner factor beta sigma and will increase, and the vertical stress will increase compared to rough turning and black material. And then the intensity factor, beta Q, the effect of surface treatment on vertical stress is measured by intensity factor beta Q, and some intensity factors under different surface treatments are listed in table 2.4 on page 38. Okay. There are 4 main factors to affect the endurance limit of element, and the factors of this factor can be evaluated by combined influence factor K sigma. We use this K sigma can be expressed as this, and the K sigma, this is the stress concentration factor. Epsilon sigma, this is the size factor. Beta sigma is the surface condition factor, and beta Q is intensity factor. Okay, and then the actual endurance limit of a meshing element will then be sigma -1 for element is equal to sigma -1. This is for material over the combined influence factor K sigma, and this is the actual endurance limit for element, and this is the endurance limit for material. Below that, if the stress concentration factor increase, if this increase, and the combined influence factor will increase, this will increase, and then the sigma -1e, the endurance limit for element will decrease, and then the epsilon sigma, the size factor increase. If this increase, means the size of the element will decrease, and then the combined influence factor will decrease, and then the endurance limit of element will increase. And for beta sigma, the surface condition factor, if this factor increase, and the combined influence factor will decrease, and then the sigma -1e will increase. And for beta Q, the intensity factor increase, the combined influence factor will decrease, and then the actual endurance limit of element will increase, okay? And then the measures to improve vertical strength for meshing element, we have 1, reduce stress concentration. Reduce stress concentration is to reduce the concentration factor, okay? And then reduce material defects. Reduce materials defects means to increase the size factor, and then improve manufacturing quality. When the manufacturing quality increase, the surface condition factor beta sigma will increase, and then use surface treatment. Use surface treatment, the intensity factor beta Q will increase, and then the actual endurance limit of element will increase. So, which of the following is not one of factors affecting endurance stress of an element? A. Stress concentration. B. The size of the element. C. The magnitude of the load on element carries. D. Materials and their heat treatment. So we choose which one? A, B, C, D. Choose which one? Which is not the factor affecting endurance strength of an element. We choose which one? A, B, C. We choose which one? Choose which one? A,
What
B,
about
C,
C, Lauchi?
Laushi D.
D. D. Okay, let me say. The four factors. K sigma is the stress concentration factor. And epsilon sigma is size factor. And this is surface condition factor. And this is intensity factor. And intensity factor, you can use surface treatment to increase. So stress concentration, we have stress concentration factor K sigma. Size of the element, we have the size factor epsilon sigma. Materials and their treatment, heat treatment. Heat treatment will use this beta Q to increase. So the answer is C. Answer is C. The stress concentration will affect the endurance stress concentration. For example, the shoulder on the shaft. Okay, shoulder on shaft will decrease the endurance stress. The size of the element, we have this picture. This with the size increase, this factor will increase. This factor is size factor. This will decrease. Okay, so the size will affect the endurance strength. Okay, and materials and their heat treatment will increase the endurance stress. This intensity factor we use heat treatment will increase the stress. Okay. So the answer is C. Okay. When the section shape of the element is fixed, the section size increase, then the vertical stress will increase or decrease. So it's the section size increase.
Limit is fixed.
Yes, the section shape is fixed. and then the section size increase, and then the vertical stress will increase or
Increase. Hey,
with the section size increase. With the section size increase, we have a picture. Okay, this with the size, their size increase. Okay, increase, and then the size factor will decrease. Okay, epsilon theta will decrease. Okay, then we have, if this factor decrease, the
also decrease.
limit will decrease. Okay, will
Yeah.
decrease. So the answer is B. The vertical stress will decrease because with the section size increase,
Laoshi, these things is really hard and complex.
what?
These things increases and decreases. Everything is related to each other. So these things, I think, is complex.
Oh, sorry, pardon, I can't hear you.
I said, Laoshi, these things, everything is related to each other, right? So I think sometimes it's complex to understand.
Okay, it's complex to understand this question.
Yeah,
This
also
is-
that one.
On that one is okay. The section size increase. Section size increase means the size factor epsilon theta will decrease. Okay. If this factor decrease, and the combined influence factor, this will increase. Okay.
Yeah.
This increase means the
Is
sigma
decrease.
minus 1e will decrease.
Decrease.
Sigma
And
minus 1e is the Hindrance
a-
limit of the element. Okay.
Okay,
So with
sigma,
the size
sigma minus
increase,
1 is not
the
fatigue strength.
is decrease. So the answer is B. Okay. Any problem?
Okay, no
Okay.
problem.
Yes, the vertical stress will decrease. Okay. And then the vertical stress of parts will increase or decrease after quenching and shorter peeling. After the surface treatment, the vertical stress will increase or decrease.
Increase.
Yes, will increase. Will
Oh.
increase. Yeah. Will increase. Okay. And oh, it's the same. It's the same. Okay. And then the actual endurance limit of an element can express as this. The sigma minus 1e is equal to sigma minus 1 over the k set. K set is the combined influence factor. So the curve should be modified. Okay. And then the modified line AF modified to line A1 F1. And this is the equation for EF and AF. And for line EF1, we have this. The stress amplitude of element plus the mean stress of element is equal to the yield stress. Okay, and the coordinate of point A is 0, sigma minus 1, and the coordinate of point A1, this point is 0 and sigma minus 1 over k sigma. And then the coordinate of C changes to C1. C changes to C1, this. Okay. And then we can obtain the line equation for A1, F1, this. Okay. And we know the the equation of line E F1 and A1 F1. A little different from this, okay? And then, like static stress state, the stress criteria fluctuating stresses is also the calculation safety factor should larger than the allowable safety factor. And the calculated safety factor is defined as the stress material stress, the stress limit divided by the maximum working stress. Okay, this is for the fluctuating stresses. Then we have this, the working point M, and the coordinate of point M is sigma M, sigma A, okay? Sigma M, sigma A is coordinate. And then the maximum working stress is the maximum stress is the sum of sigma M and sigma A, okay? Sigma, the maximum stress is sigma M plus sigma A, okay? This. And then we use this to calculate the safety factor. So we should know the sigma limit, means the endurance limit, okay? And in the location of endurance limit on the line A1, F1, E can be determined, the safety factor can be easily obtained, okay? And then we consider it in 3 cases. The stress ratio is constant and the mean stress is constant, or the minimal stress is constant, okay? And this is the stress in most shafts. The stress ratio is constant, and this is the stress in vibrating loaded spring, and this is the stress of the bolt on the variable axial load. And like this, the 3 cases, okay? If the stress ratio is constant, stress ratio is constant, okay? Then we connect the origin O and the point M and extend the line to intersect with the endurance limit line A1, F1 at point M1, okay? The M1 is the intersection point. Then we have this for this line, O, M, M1, we have this, the sigma A over sigma M is this. The stress ratio R is constant, so this is constant. Okay. And then points on line MM1 have the same stress ratio as that of working point of M. Okay. And then the coordinates of M1 can be found by solving two line equations of A1 F1 and O M1. Okay, and this is the equation for line A1 F1, and this is the equation for line O M1, and then we have this safety factor. The safety factor is the limit stress over the maximum stress, and then we can calculate the limit stress. Calculate the limit stress and obtain this. So this should larger than the allowable safety factor. So when the stress ratio is constant, the safety factor should satisfy this. Okay. And when the mean stress is constant, and then points on the vertical lines through the working point M, that is MM2, represent the same mean stresses. Okay, and then we also can obtain the coordinates of M2 and the vertical stress for constant mean stress is, we have this, the calculate factor, safety factor should satisfy this, and this is under the condition the mean stress is constant. And if the minimal stress is constant, we will do a line. It's 45 degrees through point M, and then we obtain the coordinate of M3, and this line represents the stresses have the same minimal stress, and we have this, the safety factor should satisfy this. Okay, and in these three cases, if the intersection is on line EF1, the element will yield rather than vertical. The stress is then calculated by this. The calculated safety factor should satisfy this. And this is the conditions for three. This is the safety factor for three conditions. Okay. And let's see the exercise. An element has a maximum stress. The maximum stress is 300 megapascal and the minimum stress is 100 megapascal. And the yield stress sigma S is 800 megapascal. And the endurance limit of vertical stress sigma minus 1 is 420 megapascal. Push sigma is 0.4. The combined influence factor K sigma is 2. And R is constant. The stress ratio is constant. So to calculate the safety factor, so we use which when the R is constant, we use this to calculate the safety factor. Okay. We have R is constant and the safety factor should satisfy this. And then the calculated safety factor is sigma minus 1. It's a little wrong. Sigma minus 1 over this, then combined influence factor times sigma A plus push sigma times sigma M. Below that, sigma minus 1 is 420, and the combined influence factor K sigma is 2, and push sigma is 0.4. Okay, and now we should calculate the sigma A and sigma N. We lose the maximum stress and the minimum stress. Then we calculate the stress amplitude and the mean stress. With this is the stress amplitude, and this is the mean stress. And then we can calculate the safety factor is 1.5. Okay, any problem? Any problem? This is for the condition. The stress ratio is constant. If,
Good.
okay, if there is the okay, if we change the condition, if it's the mean stress is constant, we can use for mean stress. Yes, we should use this to calculate the safety factor. Okay, if the minimum stress is constant, we use this to calculate the safety factor. Okay. This is for the exercise. And loads. When it is difficult to determine the possible variation of stresses, use R is constant to start the calculation, and an equivalent set of formulas also hold for cyclic shear stresses. For cases involving fluctuation, torsional shear stresses, substitute sigma with tau. And then when the number of cycles is less than the critical number of cycles that is in this range, the endurance stress at the number of n is this instead of sigma r. Sigma r is the endurance stress at the number of n0. Okay, but for finite finite stage, we use this sigma r n as the endurance stress. Okay. And if the endurance limit is located around the point F in the sigma m sigma a diagram, both vertical stress and static stress need to be calculated, and the vertical safety factor can be obtained by either a graphical or analytical approach. Okay, and this is an example.
Oh shit, I can't hear. No sound.
Oh, can't hear me?
Ah, yeah, now I can hear. I can.
Oh, okay. Let's look at the example. An alloy shaft carrying a maximum stress. The maximum stress is 480 megapascal. At critical section, must operate at least the 60 power of 10 cycles at a stress ratio of R is 0.25. The stress ratio R is 0.25. And the material has properties of the sigma -1. Sigma -1 is under a stress with a stress ratio of -1. Okay. The sigma -1 is 480 megapascal, and the yield stress is 800, and the push sigma is 0.2. Select the critical number of a cycle as N0 is this, and material constant M is 9. Assume the combined influence factor K sigma is 1.5. If the allowable safety factor is 1.5, determine whether the element will meet the strength requirement. Means the calculated safety factor should larger than the allowable safety factor 1.5. Okay, so we should calculate the safety factor. Okay, and then calculate stress amplitude and mean stress. Calculate sigma A and sigma M. We lose the maximum stress and lose the stress ratio, so we can calculate the minimum stress, the mean stress, and the stress amplitude. Okay, any problem? We use the maximum stress and stress ratio to calculate the minimum stress, mean stress, and stress amplitude. Okay, any problem? Okay, and then calculate vertical stress safety factor by infinite life. For infinite life means the number of cycles is N0. Okay, it's N0. Use this to calculate, and this is under the condition the stress ratio is constant. Okay, stress ratio is constant under the infinite, and then we lose the sigma -1 and lose the combined influence factor and the push sigma, and we calculate the sigma A and sigma N, and then we calculate the safety factor is 1.45. It's less than the allowable stress safety factor. Okay, the allowable safety factor is 1.5, so this count satisfy. Okay, and then calculate vertical strength safety factor by finite life. Then we should use this sigma minus 1 n. Okay, and we use this equation to calculate the sigma minus 1 n. The n is this n is at least the 60 power of 10. Okay, and then we calculate the sigma minus 1 n. We load that the sigma minus 1 and load the m is 9 and n 0 and n, and then we can calculate the sigma minus 1 n, and then we use this to calculate the safety factor, and there is not sigma minus 1, it's sigma minus 1 n. Okay, and then we calculate the safety factor is 1.88. It's larger than 1.5. And it's larger than the allowable safety factor. So, and then calculate safety factor by the static stress. Okay, for the static stress, we have the safety factor. We use this. Okay, use this, and it's 1.67. Is larger than the allowable safety factor. Okay, and then below that, for finite cycle and static stress, this element is safe, but for infinite life, this element is not safe. Okay, any problem? Okay, any problem?
Okay.
Any problem?
Any more part?
This is for 3 conditions to consider the vertical stress safety factor under infinite life and finite life or static stress. So this this element can so this designed element under static stress is safe, and under fluctuating stress with finite life is safe, but under influating stress with infinite life is not safe, because the calculated safety factor is less than the allowable safety factor. Any problem? This is for the condition, the stress ratio is constant, and when the when the life is finite, we should use sigma minus 1 n to calculate the safety factor. Okay.
Okay,
Okay.
老师。
Okay. Okay. Let's review this class. Okay.
Okay, 老师。
Okay. And we have load the vector of safety, and we studied the 4 criteria, the strength criteria. Okay, the working stress should less than the allowable stress. Okay, and then means the safety factor should larger than the allowable safety factor, and the rigidity criteria, life criteria, and wear criteria. And then we lost the classification of stress. Okay. And five parameters of the cyclic stress: the maximum stress, minimum stress, mean stress, stress amplitude, and stress ratio. Okay, 5 parameters you should master, and you should master the calculation. Okay, and then we have four patterns of cyclic stress. The completely reversed stress, when the stress ratio is -1, and the repeated stress, the R is 0, and the static stress R is 1, and the fluctuating stress, the R is larger than -1 and less than 1. Okay. So this is the type of stress. And then for the safety factor, when the stress is static, you should master the static stress for uniaxial stresses. Okay, uniaxial stresses, we use this, this is use the strength criteria. Okay, and for ductile material and brighter material, the limit stress we choose the limit is different. For ductile material, we choose the yield stress as the limit stress. But for brighter material, we choose sigma B as the limit stress and use this over the allowable stress. We can calculate the allowable safety factor. We can calculate the allowable stress. Okay. And this is the safety factor for static stress with uniaxial stresses. Okay. And then we study the orting, the safety factor under orting stress, and we load the vertical, the 3 parts of the vertical surface. Okay, and then we should master the stress life diagram. The stress life diagram, then we can use this curve to calculate the endurance limit. Sigma Rn at n is the endurance limit on the finite life in the range CD. Okay, in the range CD. use these equations to calculate the endurance limit, and then and then you should master the endurance limit diagram. For this diagram, the life is the same, means the cyclic number is the same. Usually it's the n0. It's the for this endurance limit diagram, the endurance limit is for the infinite life n0. Okay, and we know that the endurance limit of material and element is different. Okay, it's different, and the points in Z0, A1, F1, EO is safe. It's safe. Okay, and then we lose the factors to affect the endurance limit of element. Okay, four factors. This is concentration factor, size factor, surface condition factor, and intensity factor. Okay, and then for the fluctuating stress, how to calculate the safety factor? So we should obtain the limit stress. Okay, limit stress. For static stress, this is we have low is sigma B or sigma S. Okay, and for the fluctuating stress, we consider three conditions. The R is constant, or the mean stress is constant, or the minimum stress is constant. If R is constant, we use this to calculate the safety factor, and the calculated safety factor should be larger than the allowable safety factor. And this is for the element with infinite life. If the element is under finite life, we should use sigma -1 and not sigma -1. Okay, and this is for the mean stress is constant. We use this to calculate the safety factor, and it should satisfy this to the larger than the allowable safety factor when you design the element. And this is for the minimal stress is constant. Okay, and these three equation is under the condition the element with infinite life. Okay, if it's finite life, you should use sigma -1 and to calculate. And then we usually should consider the safety factor under the static stress state. If this the intersection is on line EF1, so we should consider the static stress state. Use this. Okay, so okay, this is all for this class, and this is the practice. I have give you the answer. The calculated safety factor is 1.31.
Yes, Lodge.
Yes. But but then you after class you should calculate it, this safety factor by yourself. Okay.
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 Laoshi.
And yeah.
Okay, we will.
And if you have any problem, you can send the question to my email. Okay.
Okay,
Okay,
Laoshi.
please send us the
Yes.
email.
Okay. So the class is over. Okay.
Laoshi,
Yeah.
the discussion, please.
What?
The discussion.
Sorry, I can't hear it clearly.
Laoshi, I wanted to ask why we can't have live class.
Sorry.
I wanted to ask why we can't have live class in the classroom.
Okay. Okay. Uh,
I think it's a decision from the office.
Please let us
Yeah.
know.
okay, so we can discuss it on the WeChat. Okay.
Okay, Laoshi, please accept my
okay.
WeChat.
Okay. Okay.
Thank you very much.
So class is over. Okay.
All right.
Okay.
Yeah.
Goodbye. See you next time.
Oh,
Okay,
see you.
Laoshi. Goodbye.
Bye-bye.
Okay.
Laoshi.